Welcome to today's Explainer. We're jumping right into something that honestly sounds like it was pulled straight out of a sci-fi blockbuster. We're looking at some incredibly groundbreaking research on what's called the active chassis. We're talking about completely abandoning the idea of dumb, static buildings. Instead, researchers are proposing an artificial, structural organism that's literally built to survive the crushing, violent environment of the deep ocean's pelagic zone. Let's get right into it.
So, this brings us to the central conflict established at the very beginning of the research. How in the world do you build a home in the ocean when the ocean's sole purpose seems to be destroying absolutely everything we put in it? Traditional offshore infrastructure, think oil rigs, faces this relentless, unyielding combo of saltwater corrosion and just catastrophic wave strikes. Basically, if the salt doesn't eat it alive, a massive wave is eventually going to shatter it.
Okay, let's dive into this because the researchers are proposing we flip the script entirely. The old, outdated paradigm relies on static, rigid bulkheads and, constantly patching things up with manual epoxy repairs. It's just a losing battle. The new approach detailed in the paper is this dynamic, active chassis featuring autonomous swarm healing. So instead of a dead steel cage just sitting there taking a beating, the infrastructure acts as an anticipatory organism. It adapts, it heals itself, and it actually braces for impact.
Now, to make this artificial organism work, it obviously needs an anatomy, right? And that starts with this total mouthful of a definition: graphene functionalized shear-thickening fluid, or GFSTF for short. Let's translate this highly technical term into a simpler anatomical metaphor. Think of this specialized fluid as both the reactive skin and the skeleton of our ocean habitat. Normally, it flows just like a regular liquid, but the second it experiences sudden mechanical stress, like, say, a huge wave crashing into it, boom, it instantly transforms into a highly rigid solid.
Let's take a look at the exact recipe for this incredible material. 45% of the matrix is a carrier fluid packed with pristine 1 to 3 layer graphene. This graphene basically acts as a microscopic liquid rebar to give the fluid immense tensile strength. Then, another 45% is made of tiny silica nanoparticles. And finally, the last 10% is isotropic neodymium powder. That neodymium dust is actually a magnetic material, and it provides a brilliantly clever ferromagnetic anchor mechanism that we'll see in action in just a second.
Now, for the math and physics fans out there, the fluid obeys the specific power law model for dilatant behavior. Conceptually, that flow behavior index being greater than 1 means we get immediate nanoparticle jamming under shear rates. But, in plain English, it means the harder a chaotic wave hits this fluid, the harder the fluid instantly pushes back. It is perfectly proportional reactive armor.
But, you can't exactly just paint a habitat with raw, heavy liquid and expect it to actually stay there underwater. So the researchers devised a really smart way to encapsulate this armor. The heavy defensive fluid is wrapped up in microscopic rigid plastic spheres, specifically these micro-capsules just 50 micrometers wide. To put that into perspective, that's thinner than a human hair. These tiny spheres are then mixed into a rapid curing marine rubber. This completely isolates the heavy armor from the environment and turns the whole thing into a highly stable, pumpable fluid.
So how exactly is this pumpable armor applied? Well, enter the habitat's immune system, a swarm of autonomous magnetic crawler bots executing this continuous 3-step process. First up, electrostatic deposition. The structural steel is grounded, so when the bots spray the charged fluid, it perfectly wraps around the underwater pylons with absolutely zero overspray. Second, once that's on, the marine rubber cures instantly, creating a flexible, waterproof skin. Finally, the crawler sweeps a high-intensity electromagnet over the surface. Remember that neodymium dust we talked about? This aligns its magnetic domains, permanently locking the fluid directly to the steel hull. It's just wild.
But of course, an immune system needs a brain to tell it where to go. The swarm bots are directed by a decentralized, neuromorphic control architecture called frequency-governed self-graph reasoning, or FGSGR. Operating on what the paper calls the free energy principle, this brain constantly calculates how to minimize structural surprise, which actually is just a very fancy way of saying it constantly predicts and prevents catastrophic failure before it happens.
Now, what's really fascinating about this is how the diagnostic router literally hears the future. Acoustic sensors on the submerged pylons constantly feed environmental noise straight into the brain. Using 2D and 3D Fourier transforms, it mathematically decomposes the chaotic roar of the ocean into predictable, neat little sine waves. It can calculate the amplitude, the frequency, and the exact timing of a wave strike before the massive wall of water is even visible on the surface. It even independently recalibrates its fluid viscosity predictions for temperature drops, like during the nocturnal midnight shift. Unbelievable, right?
So the crucial point here is how this incredible predictive data is actually used. The brain's cognitive states map directly to the physical behavior of the swarm. In state 1, the baseline, bots just perform routine patching. As frequencies elevate, state 2 pushes them right to the splash zone. State 3 preps for local storms, while state 4 physically locks bots onto the joints for severe hurricane conditions. And then there's state 5. This is the nightmare scenario, a rogue wave requiring total maximum kinetic hardening.
As that grid escalates, the embedded steel hull actually starts flexing its literal muscles using a triple redundant transducer array. First, magnetic coils locally alter the viscosity of that neodymium fluid. Then, piezoelectric acoustic thin films fire ultrasonic waves to perfectly match the acoustic impedance of the incoming ocean wave. And finally, a carbon nanotube mesh woven right into the skin provides an electrical field that triggers immediate surface-level rigidity. The structure doesn't just sit there taking hits, it actively fights back.
Now, an organism that can defend itself is great, but it also needs to, eat and breathe. So let's transition from the defensive anatomy of the active chassis to its metabolism. The paper outlines how this living architecture sustains itself totally off-grid, and the secret ingredient here, once again, is advanced 1 to 3 layer graphene integration. This is just an incredibly elegant closed-loop life support system. The structure powers itself using a hydrogen microgrid, storing hydrogen in metal alloys doped with graphene for super high surface area storage. The waste heat from this process, it's captured to keep the human residence and an aquaponics greenhouse perfectly warm. For water, engineered graphene nanopores provide atomic-scale salt rejection, creating a highly efficient desalination plant. And the plants in the greenhouse thrive on a nitrogen cycle that's purified by graphene oxide filters. It is total 100% resource autonomy.
Part 5. The escalation to impact. Let's move ahead and see how this all builds together when the system faces the ultimate threat. Imagine a massive storm brewing in the deep sea. At 8 p.m., it's a nocturnal calm. The bots are on the midnight shift, just running state 1 baseline repairs. But by 11:30 p.m., the acoustic router hears a deep, chaotic rumble miles away. State 2 alert is triggered. By 2 a.m., the massive swells arrive and hurricane parameters are met, aggressively pushing the system into state 4 active defense. Then, at 3:15 a.m., the sensors detect a terrifying anomaly, a massive, towering wall of water. A catastrophic rogue wave is incoming. State 5, maximum hardening, is officially engaged.
The tension in the structure right now is just immense. In these critical, heart-pounding moments before impact, the swarm bots have completely abandoned their routine maintenance. They mass migrate to the primary load-bearing bulkheads and physically lock themselves onto the highest stress joints. The system drives maximum localized electromagnetic fields, magnetically clamping the fluid-filled polyurea skin to the steel so violently that it simply cannot be ripped away by the severe mechanical strain that's about to hit.
And then, impact. A catastrophic rogue wave strikes the habitat with literally millions of pounds of chaotic kinetic force. Exactly at the millisecond of impact, the brain synchronizes the robotic swarm and all embedded transducers to maximize every single local electromagnetic and acoustic field.
And this brilliantly illustrates the exact physics of survival. At the precise moment of impact, the massive mechanical stress of the wave flexes the marine rubber skin inward. This instantly compresses those millions of tiny micro-capsules. The shear-thickening fluid inside is violently agitated, immediately driving it to a rigid, solid state. Because of the embedded graphene acting as microscopic rebar, the kinetic energy of that rogue wave doesn't snap the steel. No, it's safely dissipated laterally across the fluid's graphene web. The wave passes, the fluid relaxes, the organism survives. It's just a triumphant fusion of chemistry, robotics, and artificial intelligence. I actually want to read this conclusion verbatim from the source material because it perfectly captures the magnitude of this breakthrough. By integrating micro-encapsulated nanomaterial rheology with decentralized predictive cognitive processing, offshore infrastructure ceases to be a degrading victim of the marine environment. We aren't just fighting the ocean anymore, folks. We are dynamically adapting to it. We've looked at a massive leap forward for ocean architecture today, but I want to leave you with this really provocative thought. If we can build a self-healing artificial organism that conquers the violent limits of the deep ocean, where else in the universe could this exact same architecture take us? Think about the implications for deep space or even other planets. Thank you so much for exploring this fascinating material with me today, and I'll see you next time.